All right, good morning. We're going to go ahead and start thinking about the next part of the virtual machine translator. So this assignment for chapter 8, I'm actually going to have you submit it in 2 separate parts. And the reason for this is that a program that passes the first 3 test cases won't necessarily be a program that passes the last 3 because there's some extra things that you need to do between them. So there's some bootstrapping code that you're supposed to put in place before doing the last 3, where you actually perform a function call. So what I'm going to have you all do is first submit a version that doesn't attempt to implement function calls. And then I'm going to be able to grade that on the test cases that don't care about function calling. Then you're going to implement a version that does do the function calls. And that one I'll test on all of those. So the timetable is similar to the last project. It's just broken up into these increments. So the first part will be due Monday night, and the second part will be due Wednesday night. So I'm going to go into detail about what that distinction is, but for your time management purposes, I want to make sure that you've got these distinct deadlines in mind. And it's partly because it'll make it easier for you to make progress on this, to work on it incrementally, and partly it'll make it more straightforward for me to grade it because I don't have to worry about going in and handicapping and your fully working version just to pass the first 3 test cases. So logistically, that's where we're going from here. Any questions about that? Okay, so let's think conceptually. Well, before I dive into this next part, any questions remaining after having done chapter 7, project 7, about the stack, arithmetic, and so forth? Memory? Okay. So starting in this chapter, yeah, oh yes, V.
Yeah, I don't know. We had to store some value in RAM 13.
Right.
Why is
So RAM 13 is just a place where you can stash values when you run out of register space. That was the only reason. Yeah, it's just a place where you can stash something when D gets too busy. Yeah, that's all. Good question, good question. And you can certainly make use of those in this assignment as well if you find them handy. All right, so the programming model for the virtual machine is that everything's a function. So everything's a function, and all communication happens through the stack. Those are the 2 premises upon which the virtual machine rests. Communication through the stack, you've already done a lot of work about that. That is, you copied values from memory onto the stack. You copied values from the stack into memory. And importantly, you wrote arithmetic routines that manipulated values on the stack and replaced them with other values on the stack. So we're going to build on all of those ideas here in chapter 8. Specifically, by thinking about everything as if it were a function, we have a clean and transparent way to handle all manner of abstraction and interaction and so forth. So what is it that we mean by this? I've gone over this idea before. but it sets the stage for what we're going to be thinking about here. Every time we perform a function call in almost any programming language, we need to somehow save the computation that was intermediate when we made the call. And the way this is routinely done is to push the state of the current function onto a stack. So if I've got some function f that does some things and then calls some function g, and then g does some things and calls some function h, at this moment where f calls g, it's essential that everything we have about f be saved perfectly so that when g exits and f resumes, it can pick up right where it left off. Once we're inside of g, if it calls some function h, again, all of that state needs to be saved so that g can pick up right where it left off. And conceptually speaking, there's no limit to this process, right? H, in turn, might call some function j, and so forth. Conceptually, then, we can picture that the state of each of these functions is stored on a stack. The idea being that as a function completes, its state gets removed from the stack, and the function that's now on top of the stack is allowed to resume. The last in, first out concept of a stack is absolutely essential here. And what makes it essential is the fact that the last function called, the most recent function called, is going to be the first one to finish. The oldest function called is going to be the last one to finish. So that's the overarching conceptual framework we're going to be employing here in thinking about how the VM works. Everything's a function. Everything we think about relates to who is the current function? What's the current function trying to do? What data is the current function manipulating? And so forth. Any questions so far before we go to another level of detail? All right, so we're going to go to another level of detail. So if everything's a function, that would imply that a program has to start first by calling a function, right? And so ultimately, where we're going with this project is that the very first bits of assembly code generated will involve performing a function call. That is, there's going to be some master function that's always the first thing called. This should not be too foreign an idea. For example, when you're programming in Java, what's the first function called no matter what? Main. Yeah, and whenever you're writing a Java program, you know whatever else you do, where it starts is main. In other words, that Java compiler generates code that no matter what else happens in the program, the very first thing it does is it's going to call main. So our VM is going to do the same thing. The very first thing that does, of course, after setting up the stack pointer. So it's going to set up our stack pointer. But then the very next thing it's going to do is it's going to call a function named sys.init. So sys.init is always going to be the starting point for any VM program. Ultimately, every VM program needs to have a function named sys.init, because that's what the translator is assuming the starting point is going to be. Incidentally, this is how it becomes feasible for our VM translator to compile multiple VM files into a single outgoing ASM executable. That is, One of the features we're going to work on this week is that you need to be able to provide it with a folder, a directory. And then it's going to go through that directory, and every .vm file it's going to read in, and all of them put together, it's going to generate a single ASM file for. Part of the convention then is that exactly one of those VM files needs to be named sys.vm. And in it, it's going to have a function named init. So it doesn't really matter what order we read the VM files in. It doesn't even matter what order we generate the assembly code for them in. Because the very first thing your program is going to do is call sys.init. Function named init inside of sys. And that's how it kicks everything off. This greatly simplifies our conceptual framework because it's always inside a function. It's never not in a function. Any questions so far? Yes?
I believe that if you create like multiple Java classes and give them all main functions, the program is still going to run. What happens when you have multiple main functions in multiple different classes?
Oh, in Java? So the way Java works, when you start it up, you have to specify which class's main you want to use. And so even if every class is sitting on a main, Java requires you to say, this is the class where everything starts. This system is just going to say you need to have exactly one file named sys.vm, and it needs to have exactly one function named init. And if it doesn't have those things, it's just not even legal. Now, ultimately, where we're going to go with this is that there's going to be a sys program which contains routines from this computer's operating system. And so user programs won't even have a sys.vm. It's going to be more of an operating system thing. And then the operating system will call the user code. So this particular mandate winds up being very low level in practice. But from our point of view of building the VM translator, that's the way we think about it. Other questions so far? All right. So what is it then that we're going to implement this week? Superficially, it's not very much, but of course, it'll be quite a lot in practice. We're going to implement a statement called label. And so this will take as an argument, well, a label, not in quotation marks, so it'll just be a literal bit of text. And if we've got labels, well, we might want to go to those labels. So we can also go to a label. And that's an unconditional jump. It'll always jump there. And then we will have if go to a label. So what's the difference between go to and if go to? If go to is going to pop the stack. And if it got a true, then it'll jump. So those are what are called program flow commands. Ultimately, these commands are how things like if statements and while loops are going to be implemented. Let's just say I strongly recommend you start with these. So the first two test cases will only be using these VM instructions. I think you're going to find them very straightforward to implement. Label in the VM should then just spit out a label in your ASM code. goTo is going to be an unconditional jump. And if goTo is going to pop the stack, load the popped value into the D register, and then perform a conditional jump. So none of these will involve generating a large amount of ASM code. Of course, having all of these in place is going to greatly increase the functionality of the VM language. So any questions on those? So those should be pretty straightforward. Like after class today, you could sit down for about 20 minutes, I think, and these should be done. Does that make sense to everybody? You all see how straightforward it should be to do these? Like, you all should be passing the first 2 test cases by lunchtime. Any questions on those? Yeah.
I think I have a question, mainly because in the first part of the VM, I was having trouble implementing like equal and less than and greater than.
Right.
Which I strongly believe this thing might kind of have something to do with it. So something like JGT, JLT, those commands that we learned in assembly.
Yeah.
And I'm not quite sure how you kind of code them depending on the condition.
So in this case, it's going to be straightforward because when if goTo pops the stack, what are the possible values on the stack it cares about? 0 and -1. So you pop the stack, and you're basically going to jump if it's not equal to 0. So it's jumping if the condition is true, right? If the condition's false, it's all zeros. So if you jump if it's not equal to 0, you're good.
I guess my question was about like things like JG, JET, like greater or equal.
JGE?
Yeah, something like that. How would you?
I mean, it's not immediately relevant for translating this instruction, right? Because the VM is basically giving us actually less power than the machine language for jumps. The machine language can distinguish from 6 different conditions. The VM language basically just says, if it's true, jump, otherwise don't. So it's depending on a previous statement being an LT, a GT, or an EQ, where it pops the stack, compares, pushes true or false, and then it jumps after that. So this is actually simpler than the EQ, GT, and LT instructions from last time. Does that help answer your question? Great. Cool. Any other questions about this before we start talking about functions? All right, time to talk about functions. So there are 3 more instructions you'll be creating, and these are all for functions. So the first is called function. And function needs a couple of parameters. The first parameter is the name of the function. You know what? The book calls it F. I'll just call it name. And now it takes an additional parameter n, where n is the number of local variables in the function. So ultimately, the compilers that we write are going to figure out how many total local variables are in a function before it generates the VM code. So you can imagine a compiler kind of taking a pass through the source code of a high-level function, counting how many local variables got declared, and placing that count right here. So that's what we're going to do for a function definition right there. So you see it define a function, that gives it a name and a number of variables, local variables. What about a call? Call also takes a name, and it takes a value we're going to call m, which is the number of the parameters that have already been pushed on the stack. So this is a very important aspect of how this virtual machine language works. If you want to call a function, you first push onto the stack all of its arguments. I want you to notice, though, that this is directly analogous to how we've been performing arithmetic. That is, before I ask it to add anything, I push my addends on the stack. Before I ask it to subtract anything, I push the values to be subtracted onto the stack. So call generalizes this convention. Before you call a function, you should push onto the stack everything you're passing to it. Something that will happen, that we'll talk about in a few minutes then, is when a function is finished, it will push its return value onto the stack. And again, that's very similar to something like add. You call add, two things went onto the stack, it processes them, it then pushes its answer onto the stack. Every function will do the same thing in the VM language. So that leads us to our third function, our third instruction, which is return. And return will return to the calling function. So these three instructions then are probably the conceptually most challenging parts of this assignment. I mentioned these should be pretty easy. These are going to take some thinking. There's actually quite a lot of work to do for these. So I've outlined what their jobs are. Let's think about these jobs in a bit more detail. Specifically, let's think about the process involved with calling a function. So the first thing is the caller pushes args onto the stack. So before you call anything, you push everything you need onto the stack. Second, call the function. Third thing that happens is the return value is on the stack. So this is all from the caller's point of view, okay? Now, this is very, very important for your implementation. Local argument, this and that, and pointer are unchanged. So from the caller's point of view, the caller made a function call. When the function call returns, the local argument, this, that, and pointer segments are unchanged. And actually, so is static, although static never really changes. However, temp is undefined. In other words, you can't rely on the idea that anything that you pushed into temp is still there after the call, but everything else should still be there. So that's how things look like from the point of view of the caller. Now let's look at the point of view of the called function. From the point of view of the called function, we have argument points to the args that were pushed on the stack. Local is filled with 0 values. This, that, pointer, and temp are undefined. This, that, pointer, and temp are undefined. So when a function begins, these segments don't have any defined values in them. But argument and local do have defined values in them. So, and then of course, so that's part 1. Part 2 is before returning, we must push a value on the stack. So putting these ideas together, this is what's called a function calling convention or a function calling protocol. That is, we're still so low level that function calling protocols aren't being enforced by the programming language. In a language like Java or Python, the protocol is enforced for you. It's already sitting there. For the VM language, in principle, you could generate VM code that doesn't follow this protocol. What we're saying to the VM code writer is that if you don't follow this protocol, we as the VM translator writers take no responsibility for what happens. Okay? That's really up to whoever created the VM code. We've defined our responsibilities, which is to generate the code that behaves in this way, provided that the conventions are followed. Yeah, innocent.
So let me ask a question. You know, in Java, there are functions that has a void distribution.
That's right.
Return anything.
That's right.
In this case, if you are translating them, what you put on the stack and what you return, it sounds like you must put something on the stack and must return something.
You're right. That's an excellent question. And the answer is, we'll just push whatever. Like, we have to have some kind of dummy value on the stack to follow the convention. So what's ultimately going to happen in our higher level language is that even void functions will just push something on the stack, like just a 0 or whatever, just for fun. And then if you call a function and discard the return value, that return value just gets popped and disregarded. So basically, we just sort of have to play games on both ends, but if we do, everything works fine. But it has the benefit of simplifying the implementation of the VM translator. In other words, if we just say every function always returns something, then it's a little easier for things that don't actually have anything to return to make up something than for the VM infrastructure to have to figure out how to handle that special case. It's easier to handle the special case at the higher level than the lower level. So that's the attitude. Good question. Good question. Okay. So if that is how things look conceptually, let's now think about, in lower level detail, how things are going to be concretely laid out in memory in order to make this stuff happen. So we're just going to think about what the stack looks like in general for a function. So this is given, by the way, on page 162 of the book, but I'm going to walk through each of those pieces here to make sure that its role and its position is coherent and intelligible to you. So the very first element of the state of a function on the stack is going to be its arguments. Note that a function begins to occupy stack space from the moment that it's called. It's not like we get to a point of calling another function and then we suddenly put all of our function state on the stack. From the moment our function is called, it lives on the stack. The stack is its home. It's just when another function gets called, that function is now living above it on the stack. So, what do we have to start with? So, if this is the bottom of our stack, the first thing we're going to have are its arguments. And we'll have argument 0 through argument n minus 1. And those will all be one after another on the stack. This is pretty intuitive, right? In the sense that whenever you call a function, you're supposed to push all of the arguments on the stack first. So all of this stuff winds up on the stack before anything else because that's the order in which the calling happens. So what goes above the arguments? The very next thing is called the return address. In other words, once the function finishes, to where is it supposed to jump back? That's what goes next. Above the return address, we have 4 saved pointers. Those are local, arg, this, and that. Now, what are those doing there? I want to back up here to our calling convention, which says that local argument, this, and that are unchanged when it returns. Well, if we want them to be unchanged when it returns, then on the stack, we need to preserve those values, right? And they're preserved in this specific order. Then above this, we have our local segment for the new function. And that'll start at 0 and go up to local variable k minus 1. And then finally, that's where the stack pointer is pointing. So the book's rendition of this stack drawing looks upside down from the way I drew it. And the reason is that the way the book organizes it is to say the bottom of the stack is at a very low address in memory, like 256. And as you push things on the stack, that goes up. So they start with low memory addresses and go downward to high memory addresses. So in their diagram, it looks like the stack is growing downward. So this is kind of the inverse of that, just because I wanted us to think about piling things up. How do things pile onto the stack? And there we are. So then at this point, we have all of the practical uses of the stack. We push things, we add, we pop things, and so forth. But below all of this is all of the essential state for the current function. All of the essential state for the current function. Any questions so far? Okay, so let's think about what it means then in light of this memory model to implement the call, the function, and the return instructions. So let's begin by thinking about what is a call going to have to do to make all this stuff happen. So the caller pushes the arguments on the stack. No problem. Call itself doesn't do this. But now the code that your VM translator generates for call is going to have to do the following. The first thing it's going to have to do is push the return address. In other words, if the return address is the thing at the bottom, it's got to be the first thing that it pushes. So how do you all think we're going to do that? Push the return address. Actually, does the term return address mean anything? Or am I just spitting out gobbledygook? Yeah, honestly.
I mean, from the way I think about it, like it kind of goes on the top of the stack. See the value that is there, and then store it in an A register or D register.
Store it what?
And stores that value in a D register.
Right, and then, but ultimately we're gonna. But where does the value come from?
Like on the memory where the stack points. Okay, push. Or when you push, you put on the stack.
So let's not worry so much about pushing at the moment as this notion of return address. Somebody tell me, what does a return address here mean to you?
Location where we call the function to begin.
Say that again, Jack?
It's the location where we call the function to begin.
It's the location where we called the function to begin with. So what happens, right? So if I'm going to do a function call, I have to specify when the function's done, where do you jump back? And so that place I jump back to, I have to push onto the stack. So when a return instruction comes along and it's time to exit the function, it can pull this from the stack and then jump back to that location. So we have to tell it, this is where we're going to return to. You know, the metaphor here, right, is how when you write a letter, you know, in the upper left corner, you have a return address. You know, just in case the letter has to be sent back. Of course, with a function call, you're always going to send back. So the return address is the memory location in program memory that the function should jump to when it's done. So in your generated code, how do you all think you're going to handle this? Where is this return address going to come from? What ASM construct do you need to use to capture the return address? Yeah, please.
So we know that every time everything that happens like in assembly need to be affecting the stack to some extent.
Right.
Yeah, there's a stack pointer somewhere.
That's
and
right.
When we do things, we put the need to operate and they come back, something like that.
Yeah.
At the beginning, we start with stack pointer. We do things and then again and then we need to go back to the stack pointer. In that sense, are we saying to return about the address of the stack pointer?
No, because the stack pointer is pointing to RAM. The return address is an address in program memory, which remember is separate from data memory. So how is it that we can find out what the return address is? What ASM construct can we use? A label, exactly. What we're going to have to do is after we generate all of the ASM code for our call, we're going to have to generate a label to represent the return address. When it jumps back, it should jump back to after we do all this setup. So we're going to generate a label, and then the value we're going to push is the value of that label. That's exactly right. So once we've pushed the return address, we now need to push local, we need to push arg, push this, and push that. So you might remember that these are, of course, just locations 1, 2, 3, and 4 in RAM. Right. So you need to push all of those onto the stack in that order. Now what we're going to do is we're going to reset arg and LCL to point at these two segments. So first, let's figure out what we're going to set arg to be. Yes. So, oh, you're counting, Jack?
Yes.
So count out loud. So how are you going to determine where arg goes?
But it's like 5 back from where we are.
Okay, so if we go 5, so this is an important idea, right? Why 5 back?
Because we have local argument, this, that, and the return.
That's right. So we have to go 1, 2, 3, 4, 5. We still need to get here.
Yeah, so in or in -1 plus some number to get to the bottom of it.
Some number to get to the bottom of it, which is correct. So let's think through that number, right? If I've got n arguments, how much further back do I have to go to get to the bottom? Yeah, V.
You take, you do something with the label.
Not quite. I mean, we know the number of arguments we have because when call gets called, one of the aspects of the instruction is that number of arguments. So fortunately, we're sitting on that information. So given that information, we basically need to calculate this offset, right? So let's start with what we already know. We start with the current value of the stack pointer because we just pushed a bunch of stuff on the stack. We now subtract 5, and the 5 represents the 5 things we just pushed. Now we need to keep it going down until we get to the start of the argument segment. Yeah, exactly. So you subtract that m value that was passed in when the call instruction was written. So that's how we decide what arg is now going to be. We start with the stack pointer. We subtract these 5. We subtract these arguments. Bam, there we are. Then we have LCL. And LCL, we can actually just set this to be the stack pointer. Because once we arrive at our function, it can push all of its local arguments onto the stack, starting there. But once it does the pushes, of course, we want to make sure that we've preserved this old stack pointer location. So to be clear then, arg is here, and LCL is going to be here. And if we set those up in that manner, we should be in good shape. We should be in good shape. So and of course, there's one last instruction that I would highly recommend. Jump to our function. Unconditionally, of course. And then, as Andre had suggested earlier, we then generate a label for a return address. So that when the function finishes, it'll jump back here and resume the program. So that's a call. That's a call right there. Any questions on call? The thing with call is that it's a large number of extremely particular details. You get one little detail wrong, the whole thing is toast. But what I hope you all appreciated from the explanation here is that every detail has a coherent purpose behind it, right? These aren't arbitrary. I mean, actually, they are arbitrary in the sense that we can make up whatever we want, but they're not arbitrary in the sense that as an integrated whole, they make sense. So if that's a call, let's look at what happens when we arrive at the function. So when we arrive at the function, we've got our function fn, right? And so all we have to do at this point is generate a label for f. Why? Because we need to be able to jump there, right? And then push 0 n times. In other words, we initialize every local variable to be a 0. And we just push n of them. What that means is that this local segment has been filled up with pre-allocated local variables. So the programming language that we're going to be implementing here doesn't have a very rich structure about scope. That is, all local variables are in the single same scope throughout the function. There's no notion of nested scope where you can have variables that are local to a set of curly braces or whatever. That said, it's not unimaginable to use a programming model like this even for that kind of a setup, where you could imagine every time you have an opening curly brace, you just set up another local variable frame on your stack. That would require then kind of an array of local pointers, which is more complexity than is actually helpful for this. But that's what would have to happen in a concrete programming language that did that. Any questions? Or oh yeah, Andre.
How exactly does like local and args store multiple variables?
Basically, they're pointers to the beginning of an array or a memory segment.
So it's like push or pop local 1, 2, 3.
Exactly. So what happens is you've already implemented the pushing and popping local 1, 2, 3. What we're doing here is just saying where local is. The function, by pushing enough values to accommodate the number of local variables, makes it possible to go anywhere in the segment you need to. The caller, by pushing all the arguments on the stack, again, makes the segment as big as it needs to be.
Like would it be able to like skip like the 1 to 3 to 5? Or is that like
Oh yeah, right. So if I've pushed 5 arguments, I can do a push argument 4, then a push argument 2. I can jump around randomly like that. Now, a related issue is, well, if I push 5 arguments and then I pop argument 7, what happens? Well, the answer is, congratulations, you just corrupted your return address, or you corrupted the start of the arg segment for the caller. So that's obviously really bad. We're just going to assume our user programs won't do that. So, right. I mean, this is a really important issue. If we want to make sure we preserve the safety properties of our implementation, we have to enforce boundary checks on the segmental references. We're not doing that for this project because the goal here is just to learn how these abstractions interact with each other. Our goal isn't to produce a bulletproof system. If it was, then every time we did a push or a pop, we'd have to have some kind of bounds checking to make sure we're staying within the legal bounds of the segment. It's not too hard to imagine how to do this, right? Coming into the function, you know exactly how many local variables there are and how many arguments there are. So you could track that in your translator, and if you saw an instruction that tried to push or pop outside that range, you would exit with an error. You would just say, this instruction goes out of bounds. And so forth. So I think you can imagine how to do that. It's just that doing that's outside the scope of the assignment. But of course, that kind of mischief is both possible and extremely common in realistic systems. Anybody ever heard the term buffer overflow attack? So Andre, where'd you hear the term?
I was actually watching a YouTube video.
Uh-huh.
Like, how you can get into databases from like a certain period.
Yeah. Yeah, it's that kind of an idea. And all of those rely on this kind of a concept of knowing the segment layout, causing an illegal push to happen that overwrites a return address. You overwrite the return address to point to a block of code that does what you want, and then you've opened up a backdoor into the system. Obviously, it takes quite a lot of work to achieve this, but if you don't have any kind of safety enforcement at the system level, then yeah, you can do anything. And people have in fact done lots of anythings. Why is it called a buffer overflow? If you think of this bounded space as being a buffer, you go past it, that's an overflow. You replace the return address, that's an attack. Yeah.
So would you do an attack like that using a high-level programming language? You need to be programming in assembly or machine language?
You would need to be programming in machine language, generally speaking. Like, the program that you're hacking could very well be in a high-level language. It's just that the code that you're trying to force it to execute needs to be a binary executable. Yeah. So if you can get the binary executable into memory somewhere, like say in a local segment or even in your arguments, then you just make it jump to that. So of course, this relies on program and data memory being the same, which is typical in a computer. I mean, our model where we have them separate has some real advantages. The advantage of combining them is you've got some wiggle room, right? If program and data memory are the same, if you've got a short program, it can store more data in RAM. If you've got a long program, it stores less data in RAM. You've got a nice trade-off you can make there. If you've got different zones of program memory versus data memory, you can't use unused program memory to store more data. But conceptually, having them separate is so much easier and obviously more secure. Yeah, it's possible in principle, right, to write machine language programs with shared program and data memory that modify themselves. That may seem insane, and it kind of is, but you could imagine writing a program that keeps track of a loop counter by modifying an argument to a branch comparison in a machine language program. You know, imagine you keep checking to see, well, have we gone 5 times, and you've got to have some memory location that's keeping count. Well, in principle, you could imagine modifying the A instruction itself to see if you've hit the limit. Yeah, it has certain disadvantages, right? Like, well, what if you jump back there? Well, you've already modified yourself. So self-modifying code isn't like a great idea, but it's something that people sometimes do when they're on highly memory constrained systems and they're trying to avoid even having to maintain a separate loop counter. But yeah, that's well outside the scope of this class. But people can do crazy, crazy stuff at the machine level. Especially if you share program and data memory. So that was a bit of an aside, but I think it helps contextualize lots of aspects of low-level systems you hear about, like buffer overflow attacks and so forth. All right, cool. We're ready to look at returns. We got any more questions about calls? So return is going to be the inverse of what we do with a call. Excuse me. So when we're thinking about the inverse, what we're going to have to do is carefully unpack the stack. So for starters, we want to keep track of where this was right here. That's going to be useful later when we start figuring out what we're doing next. We have to do some real nonsense to the stack at this point because the function has placed on top of the stack a return value. But what we ultimately have to do is migrate that return value all the way down here. Actually, no, not all the way down there. All the way down here for the caller, right? So we have to get rid of all of this stuff from the stack. But in getting rid of all of this stuff, we also, at the same time, have to not destroy it until we've used it, right? So that's going to make a return fairly complicated to implement. So let's begin being complex. So the first thing we need to do is keep track of where this bit is right here. So following the convention that's given in the book's description of this, we're going to call that frame. We're going to set that equal to LCL. So frame is just keeping track of where we find all of our saved data. And you can use like one of the memory locations 13 to 15 for this. Next, we need to snag our return value, or our return address, which we'll call ret. And again, we can store it in one of those 13 to 15 places. So if we think about finding the return address, it's at location. So let me put frame there for reference. So we set frame equal to LCL, right? So if we count down 5 spots from frame, 1, 2, 3, 4, 5, we have our return address. Oops, didn't mean to do that. So ret is going to be value at frame minus 5. And again, you would want to put that somewhere temporarily in memory. Now, the next thing we're going to do is move the return value to where the caller expects it to be. So you're going to, so a way to think about this is you can just say, pop the stack, place popped value at arg. So what we're doing, looking at this layout here, is we have a return value sitting up there. We need to pop it from the stack and send it all the way down here. Why? Because this is where the caller is going to be looking for it, right? And of course, once we do that, if we want the stack to look right for the caller, what's something else we're going to have to do? If we want the stack to look good for the caller. So the caller knows that his return value is at the top. We're going to have to change stack pointer, right? So this stack pointer is going to have to be pointing up here. In other words, arg plus 1 is going to be the new value of the stack pointer. So scooting over here, we place that popped value at arg, and now we can say that SP equals arg plus 1. So what we've done at this point is the stack now looks correct for the caller. But we still need to get all of this valuable information we saved off of the stack and into a safe place. That's why we use this frame variable up here to keep track of where all that stuff was. Because now that we've changed the stack pointer, if we try to just pop all that stuff, we're hosed, right? It's just off on the stack. Okay, so what's that going to look like? Well, because we have frame, this is actually really simple. We say that is equal to the value at frame minus 1. This is going to be the value at frame minus 2. Arg, so now we're restoring arg for the caller, right? It's just the value at frame minus 3. LCL is just the value at frame minus 4. And now we've got all that stuff restored, so we can jump to that return address that we grabbed up there. Now let me point out an important aspect of how this is organized. Let's imagine, oops. Okay, yeah, I was just shrinking that a little bit. Okay, I was trying to shrink it. All right. Let's imagine that we don't have any arguments at all, okay? So if we look back at this diagram of the stack, imagine we've got no arguments. Well, if we've got no arguments, when we copy the return value, we're going to overwrite the return address. That's why it's essential that before we do anything else, we copy the return address to a safe place. Because if there were no arguments, it's going to be overwritten. So that's why the first thing we do is we stash the return address. Then we take care of the return value. We reposition the stack. And at that point, we retrieve all of our saved information. And at that point, we have returned from a function. That's return right there. So all of this is outlined on page 163 of the book. But again, it's pretty easy to kind of see a table like that and wonder, why is it that they're doing it this way? And I hope from this explanation that's become a lot clearer. Any questions so far? Okay, so let's talk a little bit about generating names in the assembly code, given that you're doing the VM stuff. So first, let's think about label. So anytime you generate a label, it would be tempting to just generate that same label in assembly code. But we don't actually want you to do that. And the reason is that if we do that, it becomes possible to jump from inside one function to inside another function. I'm going to argue that that is bad. And why would I say it's bad if you can jump from inside one function body to inside another function body? Yeah.
Why not maybe corrupting some local argument values that respond to that one function that you are kind of embedding when you're supposed to be operating to some local argument of the function after that?
That's exactly right. If you jump from inside one function body to inside another function body, the context of the other function isn't going to make any sense. Your local and argument segments are going to be nonsensical. So we have to restrict jumps to happen within a function. So what we do is we generate a label to be function name dollar label, like that. Then the function name itself should be the name of your VM file dot the declared name. Then, of course, with the return addresses, you just have to be careful to generate a unique return address for every function call. A technique for doing that we talked about last time, you can just use a counter to generate return address label names. And that's basically what this stuff looks like, right? End to end, thinking about your virtual machine translator. You know, the thing with this assignment is once you can build a fairly coherent idea in your head about the function calling conventions and how those work, I expect you to find the implementation to be straightforward. I don't necessarily expect it to be straightforward to get to a point where the calling convention all makes sense in your head, right? It can take quite a bit of thought to get to that point, and the rate at which you'll do that will vary. Some of you will get this faster than others, and that's okay. There's nothing wrong with that. But I do want to encourage you then, of course, to start early on it, because it's the sort of thing where you can stare at this stuff and be trying to work it out and get really, really confused. And by starting early, you make sure you've got enough time to visit with me in office hours or send me email to get your questions clarified. Whereas if you start it, the day it's due, I mean, bad things will happen in many cases. So I do want you to appreciate how powerful a set of constructs this actually is, right? Once you've got all of this in place, you've created a virtual machine where you've got the ability to define functions. Every function has its own local namespace that's unique to it. It's protected from other functions. They can still share values through static variables. So, given all of this, I hope you can see how the implementation of essentially any conventional programming language would be easily realized in this framework. Obviously, it's going to take a bit more work than to just say, oh, it's obvious. That'll be chapters 10 and 11. But you should be able to visualize what it fundamentally is going to look like. Cool. Any questions? Any questions? Well, I think it's close enough to 9:30. We'll call it a day. I'll see you all on Tuesday.